Wow. Despite what I've done the last 2 weeks, you've come back. I'm glad to see you. We got nice weather. It almost feels like spring. So we're going to talk about something that at first glance may appear to make no sense to you, because we're supposed to be talking about astronomy and cosmology. So let's talk about baked potatoes. Okay? Today we're going to get an age for the universe, our first real age for the universe. And we're going to get it from baked potatoes. Okay? So what I want you to do is tell me, how do I know the age of these baked potatoes? How old is it? Okay. Let me help out. Here's a nice baked potato. Okay. What's its temperature? What's the came out of the oven or not? That's what we need to know. We need to know the temperature, but there's something else reasonably special about the baked potato, at least by analogy. So let me show you what we can do with our baked potato analogy, because most analogies in science have a lot of problems. This one actually is pretty good. So let's try. So how would we make a baked potato? Well, coat it with oil, salt, in the oven. Okay. You're going to bake it at 450 degrees for an hour, and when it's done, it comes out of the oven, the internal temperature will be 210 degrees. That's our starting point. What do you do with it? You put it on the table. You serve it to somebody. It sits on the table for some length of time. I'm going to let it sit on the table for 2 hours and 20 minutes, because that's going to make the math easy. Okay? And I'm going to let it cool from 210 degrees, about the boiling point of water, to 70 degrees, which is about room temperature. I'm going to assert that the size of the baked potato is not going to change. Have you ever noticed, as the baked potato sits on your table, that it changes size as it cools? Wrinkles. The surface of it wrinkles. It doesn't really shrink. Okay? Objects, when they cool, excuse me, when they cool can shrink. So if you have a hot air balloon, and you keep the air tightly inside the balloon, but the balloon cools, it shrivels up. The baked potato doesn't act like that. To a very, very, very small level, it will shrink, but not much. Not that you could measure. I would challenge you with that baked potato. Those of you who said the baked potato shrunk as it cooled, go home, make a baked potato. Measure the volume. Remember how you measured volume when you were in 4th grade? Okay, put it in water, okay? So fill up a pitcher with water, put the potato in water, let the water flow out, measure how much water comes out. Now, let the potato cool. Repeat your experiment. See how much water comes out. If any of you can prove to me that you can measure the difference in the amount of water that comes out during that experiment, I want to know about it. Okay? Baked potato doesn't shrink much. So I'm going to assert the baked potato doesn't shrink, because that's an important component of our experiment. So how many degrees change did the baked potato experience? 140 degrees. In how many minutes? That's why we chose 2 hours and 20 minutes, 140 minutes. Right? So our math is going to be easy. We dropped 140 degrees in 140 minutes. So what's the rate of change of the temperature? A degree a minute. Okay? You guys can graduate now. Okay? A degree per minute. Now you can measure the age of any baked potato. This baked potato came out of the oven 140 minutes ago.
So that's a linear. You wouldn't drop it.
Wouldn't drop linearly. No, you're right. It would not drop linearly. And for those of you who don't know what she's talking about, a linear drop would be 1 degree in the first minute, 1 degree in the second minute, 1 degree in the third minute. But in fact, it will cool off fastest early, and then it will cool off more slowly. That's a nonlinear process. A linear process would be the same rate of cooling for the whole length of time. Okay, remember I told you analogies don't work? Well, I guess the baked potato analogy is not as good as I'd like it to be.
The same problem in astronomy.
We do. If you want to do this right, you've got to account for the nonlinear cooling, and then we need to use calculus. And for my baked potato, we don't want to go there, right? So here's a new baked potato. We know the cooling rate for all baked potatoes, I'm going to assert this, is going to be minus 1 degree per minute. This has a starting temperature of 210 because I'm going to assert that all baked potatoes come out of the oven at 210 degrees. And this one now has a temperature of 150 degrees. How old is it? An hour. Came out 60 minutes ago. We know how to do that math because we've measured the cooling rate. We know the initial temperature. We know the current temperature. And we know the size doesn't change. Those are our baked potatoes. All right. And there's the math that you guys did in your heads. Good job. All right. So now you can tell me the age of any baked potato you want. What I want to do is find the astrophysical baked potatoes. I need to find some astrophysical equivalent of our baked potato. So what properties must my astrophysical baked potato have? It can't shrink. What else? What about the temperature? It has to have a temperature. Okay? And something that has a temperature does what? Cools. So I need to find objects that are hot enough that I can find them, and I need to measure their temperatures, and I need to measure how fast they're cooling off. All I need to do is find those objects. So let's start. Can we bring the lights down a little now, John? This is a part of the sky that will be familiar to most of you. We have Orion over on the left. We have Orion's belt. We found Betelgeuse up here last time, and Rigel, the blue giant, down here. Up here, these two stars, Canis Minor, not much of a constellation. Down here at the bottom, Canis Major. This bright is Sirius, the brightest star in the northern sky. The next image is of all of Canis Major, so keep an eye on those two so you can orient yourself. So here we have Sirius and the other star near it. Canis Major is the dog, the big dog. And you can imagine this big dog is standing on his tail. This is his front shoulder. This is his front foot. His back goes down this way. Here's his tail. There's his hind leg. His head, I guess, is somewhere up there. That's our dog, Canis Major. Sirius is the star we're interested in. In the mid-19th century, Friedrich Bessel discovered that Sirius did something very odd. In looking at this cartoon, we have a bunch of outlined stars. Those are the background stars. Those stars don't move. You go out today, tomorrow, the next day, they stay in the same place. So what Bessel did is he was watching Sirius, and he saw that Sirius cartoon slalom. It moved across the sky while the other stars stayed in the same place. There were stars that were already known that moved across the sky, but they moved in straight lines. They didn't go up and down and up and down. They went straight across. The only way, the only way that this star could be doing this loop-de-loop is if it were actually in orbit around another star. So you have two stars orbiting each other. Okay. If they stay in the same place, they just go around in circles. But if the two stars together are traveling through space, you've got this. And if you only can see one of them, what you see is a star that looks like it's doing this loop-de-loop, up and down and up and down. So there must be a second star in this system. In 1862, Alvin Clark, who was a builder of telescopes, he and his sons built most of the important telescopes in the mid-19th century. Alvin Clark discovered the companion, Sirius B. So when Sirius goes up, Sirius B goes down. When Sirius B goes up, Sirius A goes down. And together, they move across the sky. The reason Sirius A has a bigger loop is because it's a bigger, more massive star. Smaller object. Here's some images of Sirius. The one on the left is a Hubble Space Telescope image. It's a really stunning image. So Sirius, or Sirius A, the main star, is in the middle. This little dot down here, That's Sirius B. Very hard to see. These lines that come off are because of the telescope. I'll say something about that in a minute. The image on the left, same two stars. But now the two stars are seen with an X-ray telescope. And with the X-ray telescope, Sirius B is the big bright one. Sirius A is the faint one. So they produce different amounts of light relative to each other depending on what kinds of light you measure. But in visible light, the light that our eyes can see, Sirius is the big bright one. So let me say something about these lines. They have nothing to do with our talk, but everyone, or our subject, but they confuse lots of people. So here's a cartoon of a telescope. Down here, this is the main mirror. The light from the sky comes down through the tube of the telescope and hits that mirror. You've got to do something with the light. That light bounces. But it's very difficult to put your eye up there, because if you do, you're in the middle of the telescope. So you've got to get the light out of the telescope. So what astronomers have done is they put another mirror called a secondary mirror up here. The light bounces off the secondary mirror, then comes through a hole in the primary mirror, and you put your eye or your camera or your detector system down here. And since it's down here, it's out of the telescope column. You can put anything you want there, bolt the big camera on there and go to work. That mirror up there is magic. It just floats, right? You've got to hold it up with something. What you do is you hold it up with the thinnest, strongest wires you can. What these are. That's coming down through the telescope that reflects and scatters off those spider wires, as they're called. So when you see these lines in astrophysical images, what you're seeing is the optics of the telescope. You're not seeing the object itself. In the X-ray image, you have 6 of these lines. That has to do with the construction of the X-ray telescope. That has nothing to do with the object. All right? So now we can move on. In 1915, we had measurements made of the temperature of Sirius B. So it's 1915. Walter Adams makes these measurements. We know that Sirius and Sirius B are at the same distance because it's a binary star system. They're at 2.6 parsecs, whatever that means. They're about 7 light years away. Sirius has a temperature of 9,900 degrees. Sirius B, 25,000 degrees. Sirius B is the hot one. But Sirius is the bright one. It's 23 times brighter than the sun. Sirius B, 35 times fainter than the sun. Now, of course, you saw in X-rays, Sirius B is the fainter one. So it depends on which wavelength, but these numbers take into account all the wavelengths that the stars emit light. What do we get? We know, remember that Stefan-Boltzmann law? No. Okay. The Stefan-Boltzmann law told us something about what properties of a star. Anybody remember? The temperature, not the distance, the size, and there's one other parameter. Not the color. I heard something close with the heat. The brightness of the star. How much light comes from the star? Remember our pot of spaghetti on the stove. What determines how hot the burner is underneath and whether it will heat the water to boiling? The temperature and the diameter, the size. Okay? Together, the temperature and the size determine how much energy, how much heat, how much light is coming out. So the Stefan-Boltzmann law related the luminosity of a star to the size and the temperature. If we know any 2 of those 3 things, we know the third. Well, what do we know for Sirius B? We know the luminosity. We know how much energy it produces. We know its temperature. If we know those 2 things, we can determine its size. And its size turns out to be almost identical to the diameter of the Earth. Not the sun, but the Earth. Sirius B is the size of the Earth. But it's a star. It's a really tiny object. It's 4 times hotter than the sun. It's 34 times fainter than the sun, Together, those properties make it 100 times smaller than the sun. A star that's the size of the Earth. These objects are known as white dwarfs. Now remember our HR diagram. I said you're going to see HR diagrams a lot. You're going to see HR diagrams a lot. Okay? So remember we decided that our HR diagram plots brightness on the vertical axis, temperature on the horizontal axis. We have hot objects to the left, cool objects to the right, bright objects at the top, faint objects at the bottom. A hot, bright object is big. A cool, bright object is incredibly big. These are the super big objects up here. A cool, faint object is small. A hot, faint object is super small. So in the HR diagram, we knew from last time that the tiny objects are in the bottom left corner. The biggest objects are in the top right corner. As you go upwards and to the right, the objects get bigger and the sun is in the middle. So here's an actual HR diagram. This was made by a telescope called Hipparchus, which was a European telescope that was active in the 1990s. Each data point is the location of a star, and these are the 20 or so thousand closest stars to the sun. Again, the vertical on this axis, it compares these to the luminosity of the sun. So 1 is the luminosity of the sun, and there's the sun. 10 would be 10 times brighter than the sun, 100 times brighter than the sun, etc. So the faint objects are at the bottom, the bright objects are at the top. The horizontal axis is temperature, 3,000 degrees to the right, about 30,000 degrees to the left. The sun has a temperature of about 6,000 degrees, which puts the sun here, 6,000 degrees, 1 solar luminosity. All right? Sirius B sits down here. It's 34 times fainter than the sun, so we have to go down. And it's 4 times hotter than the sun, so we have to go to the left. Sirius B sits over here on the HR diagram. Sirius B is in the part of our HR diagram that we super small. Well, one thing for us to say qualitatively, they're super small. It's another thing for us to be able to measure their sizes. And with Sirius B, we measured the actual size of one of these super small objects. It's the size of the Earth. It's a tiny little object, all right? Objects are white dwarfs, so we want to know about white dwarfs. What are the white dwarfs? And this is the real challenge for us today. Step 1 was convincing you that there are objects that exist in the universe that astronomers can actually go out and identify, measure their temperatures, measure their sizes, measure their luminosities, and they're stars the size of the Earth. But what are these objects? So the hard part now is truly understanding these objects, and if you're still with me at the end of the day and you come back next week, we're in good shape because we got some tough stuff ahead of us now, all right? We want to really understand white dwarf stars. The most important thing to remember about stars is that mass matters. Mass is the most important controlling factor for stars. There are factors. If a star were made 100% from uranium, which that star would behave very close. But those two stars could have identical masses. But if they're made of different stuff, they could behave a little bit differently. Most stars are made of hydrogen and helium. A typical star is about 98% hydrogen, and the rest is helium by content. I'm sorry, 90% hydrogen, should have said 8% helium, 2% is the other stuff. 98% hydrogen plus helium. The other stuff, the carbon, the nitrogen, the iron, it's in the noise in the stars. Mostly hydrogen and helium. So they're determines almost everything about a star. Stars don't have free will. A star can't sit around saying, I think today I'm going to be hot and bright. Tomorrow, now just be cool. Okay? They can't do that. Mass determines everything about what a star will be. And our HR diagram is a great way to look at what stars So let's look at some star-forming regions to understand what's going on. Stars are born in what we call dark clouds. In the Milky Way galaxy, there are regions that appear very dark. They're dark because they're full of dust, and the light from those regions can't get out. These dark regions, if the dust were not there, you'd see just as many stars here and just as many stars here as you do in the surroundings. In between all these very distant background stars is a cloud of dust. And inside that cloud, that's where stars are born. And there are lots of these star-forming clouds. Back to Orion. You're familiar with Orion again. Inside Orion, in the sword hanging from Orion's belt, the middle star is not a star. The middle star is known as Orion's Nebula. Orion's Nebula is a star-forming region. It's a giant cloud in which thousands of stars are being born. This has taken place over the last few million years, so they're not all being born today and yesterday, but they were born steadily over a period of several million years. If we look inside the nebula and we look deep enough, we see down in here 4 stars that are known as the these 4 stars right here. They're incredibly hot, bright stars. They're incredibly massive stars. They're so bright that they're lighting up the nebula, making the whole nebula glow. They're also blowing the nebula away. So in a little while, which means in a few million years, these stars, these hot winds from these incredibly hot, bright stars will blow all the stuff away that is not collected into stars. And the Orion Nebula will disappear, and the only thing left will be all these individual stars that are being born inside that nebula. So let's talk about gravity, because gravity is why mass matters. Gravity is an attractive force. Any 2 objects attract each other. So I have 2 objects, they each have a certain mass, they go whump. Gravity attracts them together. So why don't these 2 tennis balls go whump right here, right now?
Not enough mass.
Not enough mass because what's actually in control around here? Gravity of the Earth. But the gravity pulled these tennis balls down toward the center of the Earth. If the Earth were not here, if I just had these 2 objects, the force of gravity is an attractive force. What you can do when you think of a star is you can think of a star as lots of little pieces. So let me take my star, take the sun, and in whatever chunks you want to break the sun up into, break the sun up. Break it up into 1,000 pieces and separate them a little bit. Break them up into 100 billion pieces, separate them just a little bit. And now what's going to happen to all those pieces? They're going to assemble themselves because gravity. Gravity is going to pull these 2 pieces together. Gravity is going to pull these 2 pieces together. One of the important things about gravity is the closer 2 objects to get together, the stronger the force of gravitational attraction between them. All right? So I have this cloud, this interstellar cloud, and all the molecules in that cloud are attracting all the other molecules in the cloud. So a little piece of that cloud gets smaller. When it gets smaller, what happens to the force of gravity collectively for all the stuff in that cloud? It gets stronger. Yeah. Which means all the pieces of the cloud are going to do what? Themselves together faster, which makes the whole cloud smaller, which makes the force of gravity greater, so they pull themselves together faster, which makes it smaller, which makes the force of gravity stronger, which pulls it together faster, and this whole thing collapses. And that's how stars are born inside these clouds. Can possibly stop this thing, this collapsing star, from getting any smaller? Shouldn't it just collapse until there's nothing left, until it disappears? Heat. There's the answer. What does heat do? If I have a gas and I heat it up, what does that hot stuff do? Expands. The expansion is an outward pressure, all right? As this collapsing core of this molecular cloud, this dust cloud, gets smaller, it gets hotter. As it gets hotter, it produces pressure, thermal pressure, heat, which pushes back against gravity. The birth of a star, the lifetime of a star, is a struggle between two things. Gravitational force, which is trying to squeeze the thing into nothingness, and heat, which is pushing back and trying to make the whole thing expand. If there's enough heat, gravity loses. Either gravity squeezes the object any further, or the heat is so strong, the whole thing expands. Go back to the Orion Nebula. These stars in here are producing so much heat, they're going to make the entire cloud expand and disperse, and there won't be a cloud anymore. No more stars can form in there. The thermal pressure for expansion is too great in that cloud. But in the little piece that formed these stars, heat lost. Gravity won and squeezed that object until it became a star. So we have objects that are known as protostars. These are the star-forming objects. They're collapsing. They're getting smaller. The gravitational force is in. They're collapsing and getting smaller, so gravity gets stronger. But as they collapse, the heat inside that collapsing thing increases. These hot things are going to try to radiate the heat away. In the little tips of each of these pillars, there are newborn clouds, and they're radiating as fast as they can. You make something hotter than its environment, it tries to get rid of the heat. Yes, ma'am.
What causes the heat to begin with?
Good question. Question was, what caused the heat to begin with? When these, not nuclear, okay? When two objects come together, think of this ball and the Earth as the two objects coming together, right? This thing came down, pretend it's an old tennis ball so it won't bounce. Okay? What just happened to this thing, to the surface of this? It got compressed, somebody said, momentum hit it, this thing came down and hit it. This thing was moving. As it's moving, it has a certain amount of energy. Kinetic energy, energy of motion. Now it's not moving. Where'd that energy go? Heat. Okay? So when you think of all those pieces of the cloud coming together, now break them up into trillions and trillions and trillions of pieces. They collide with each other. And as they collide, some of that gravitational, what's called gravitational potential energy, which is the energy these things have just in case gravity pulls on them, gets turned into kinetic energy, and that kinetic energy gets turned into heat. And this thing heats up. So we have a heating protostar. Because they're hot, they radiate the heat. They can't radiate the heat as fast as you to excuse me. So they get smaller. The question, when will these objects stop shrinking? These happen to be two young stars. Here's one right at the tip is another one. Will these stop shrinking? What will make them stop shrinking? And before someone in back again says nuclear fusion, I want a more general concept. What is going to stop gravity from squeezing this thing? It has to get the outward pressure from heat has to become as strong as the inward force of gravity. As long as the object is able to cool off, then not as fast as gravity can generate the heat, it's not going to work. And these objects get smaller and smaller and smaller and smaller, and they just can't generate enough heat if the only source of heat is gravity. So if gravity were the only source to heat up this protostar, it would collapse until gravity ultimately wins. It would just disappear. But it doesn't just disappear, because when it gets small enough, it gets hot enough that nuclear fusion kicks in. Nuclear fusion is a new source of heat for this protostar, and when nuclear fusion kicks in, it's a star, not a protostar. This is the definition of a star. A star is an object that generates heat through nuclear fusion. Nuclear fusion is not what's going on in the reactors in Japan. Nuclear fusion is not what's going on in any nuclear. All nuclear reactors is nuclear fission. Nuclear fission is the and when the atom falls apart, when the nucleus of the atom falls apart, energy is released. That's not what's going on here. What's going on here is nuclear fusion. Fusion objects together. The nucleus of a hydrogen atom is a proton. If I take two protons and smash them together, I can make a new nucleus. And if I do that, I get energy out. If I do that enough times, I can turn the hydrogen into helium. If I do that with helium enough times, I can turn the helium into carbon. Smash carbon together, I'll get oxygen. If I smash oxygen and helium together, I'll get neon. And you can keep building bigger and bigger. Not through nuclear fusion. Sunspots have the same chemical composition of the star, they're just cooler. Sunspots are caused by magnetic fields on the surface of the sun, which actually prevent hot stuff from coming up to replace the hot stuff on the surface. So the surface of the sun is cooling off. Cool stuff sinks, hot stuff rises. But the magnetic fields in certain parts of the sun stop that process for certain amounts of time, so the stuff on the surface cools off. Cooler than the other parts, be hot, but it looks cooler than the other parts of the surface.
And also molecules that are being thrown together to form the stars. What is the dust and what are the molecules?
Most of the dust and the molecules are hydrogen. Okay? A little bit of it's helium, the rest of it's carbon, oxygen, nickel, iron, magnesium, silicon. When we say dust, well, we mean the dust. We wipe off counters, which is mostly stuff made of silicon, oxygen, carbon, not the hydrogen and helium. The hydrogen and helium, most of it remains in the form of atoms or molecules rather than dust. Dust are the bigger structures. Yes? Do we know the impact of dark matter on all this? No? Yeah. Dark matter attracts, but dark matter is non-collisional. So if we had two pieces of dark matter, they wouldn't hit each other and generate heat. So dark matter probably provided the gravitational trigger to make galaxies form. They're not the trigger to make stars form. Okay? But the galaxy is ought to be full of dark matter, but it's not having an effect on this. At the centers of stars, that's where they're hottest. When the center of the star reaches a temperature of 10 million degrees, it's the critical temperature for nuclear fusion of hydrogen to kick in. At 10 million degrees, the hydrogens are hot enough they can smash each other. Why do they need to be so ridiculously hot? Hydrogen, protons. Protons, they have negative charge. So I have two protons. They both have positive charges. I bring them close together. What's going to happen? They repel. I can't get them close together. If I want these two protons to get close enough together to collide so that nuclear fusion can occur, I've got to make them hit really hard, because they have to be coming together so fast before they that their charges want to make them repel. So if you think of drivers on the highway playing chicken on a one-lane highway, bzzz, They're both going 90 miles an hour. Well, if one of them slams on the brake hard enough, they might stop. But if they're both going 160, by the time they see, they can slam on the brake all they want. 10 million degrees is a measure of how fast these protons are going. You get temperatures that high to make the protons go fast enough for them to collide without noticing that they actually don't want to collide. And when they collide, they release energy. And that extra energy heats up the center of the star, which provides additional heat and additional pressure to resist gravity. If the nuclear fusion reactions don't go fast enough, in other words, if the star decides, free will, right? If the star decides, oh, let's have 4 collisions today and see if that works. If that doesn't release enough heat, he's going to squeeze the star hotter, and hotter, the rate of nuclear fusion reactions will go faster. So tomorrow there might be 10 or 20 or 100 billion reactions. And if there are enough nuclear reactions to release enough heat, gravity stops squeezing the star. So now gravity has stopped squeezing the star, and the star says, oh, I don't need to do nuclear reactions anymore, right? What's going to happen if the star just produces enough energy to stop gravity and then stops the nuclear reactions? It's going to cool off, so it'll squeeze itself some more, so it'll get smaller, so it'll do more nuclear reactions. It has to keep doing this, or else gravity will win. There's a question over here. Yes? We're going to talk about dark matter and dark energy in the 6th class. So I don't want to defer it completely, but we are going to get there. Dark matter is actual stuff. Okay? Dark energy we don't understand as much, but dark energy is a repulsive thing in the universe that pushes the galaxies apart, whereas dark matter is a gravitationally attractive thing in the universe. We just don't know what it is. All right? But we are going to spend some time. Yes? The question is equals mc squared. Okay? Energy equals mass, the speed of light squared. Mass can be converted to energy. Energy can be converted to mass. We can think of the universe as being stored in different forms. One form is gravitational potential energy. One form is the energy of motion of objects. One form is chemical energy in oil or gas. One form is mass. Mass is just a reservoir for storing energy. So mass is energy. Mass is to energy. It just happens to be a storage reservoir for energy. But it's mass. Okay? When 4 protons, 4 hydrogens are brought together to make 1 helium, because it takes 4 of them to make the helium, there is less mass in 1 helium than in the 4 hydrogens. If I put them on a balance, the helium would be lighter that way. The helium would be lighter than the 4 protons by 0.7%, I think it is. Less 7,000ths, I think, of the mass. And if you take the protons and figure out what that mass difference is, that's the mass that's converted to energy. And it does come from the E equals mc squared relationship. So mass is converted to energy inside the star that produces the heat that stops gravity. The star needs to do that constantly or gravity's going to win, because gravity ain't going anywhere. But the heat continues to disappear from the star. It's hot at the core, the heat gets out to the surface radiates it away, the star loses heat. So it generates more energy at the core, nuclear fusion reactions. But that heat gets out to the surface and goes off into space, and the star cools off. And the star's going, do I have to? Okay. And the answer is yes. It has to do it forever or gravity's going to win. But it can't do it forever. It runs out of fuel. Eventually, all the protons, all the hydrogen in the core, where it's hot enough for nuclear, the only thing left in the core is helium. And it takes a temperature of 100 million degrees to make the helium fuse. And the star is not at 100 million degrees. So life has to change for the star. So down here in the core, that's where the fusion reactions are taking place. Gravity is squeezing inwards. Pressure from heat is pushing outwards. The star is in balance. It's a nice, happy object. The stars are born when the nuclear fusion reactions kick in. The reason most stars on is because that's where stars have settled in for their lifetimes. All the stars on the main sequence are in balance between gravity squeezing in and the luminosity of the star pushing back out. And as long as it remains in that balance using the nuclear fusion reactions in the core, it stays in the same place on the HR diagram. So why I'm asserting this sequence is a mass sequence. I can tell the mass of the star. I can measure the mass of the star. Let's start by talking about the extreme ends. Here we have some stars at the bottom of the main sequence. They're extremely low. They're extremely cool objects, cool, low luminosity. Why are they not luminous? What would make them become super luminous and belong at the top of the sequence? Bigger. If they're hotter, they go up there, but why should they be hotter? What would make them hotter? Fusion. If they're hotter, it means there are more fusion reactions going on in their core. Why should some stars have more fuel that's being used, but why? Why are they producing more light? Why are they hotter? Because gravity is squeezing them harder. They need to produce more light, to produce more heat, to resist the gravity that's squeezing them. Which ones are squeezed hardest? The big doesn't mean this big. It measures what? Mass. The more mass the star has, the stronger its self-gravity. The more heat it needs to resist the gravity of its own mass. So more massive stars have to become hotter and more luminous. Lower mass stars don't need to be as hot or as luminous. And we can actually calculate what luminosities and temperatures stars have given how much mass they have. But we can also go out and measure the masses of stars and test our theory, match the masses of stars. We calculate from first principles about gravity and nuclear fusion, etc. So this is a sequence which measures the masses of stars. At the above and to the left of the sun, those stars are more massive. The ones below the sun to the right, those stars. And as long as stars can produce energy from nuclear fusion to resist gravity, they're going to, and they're just going to sit there.
They all made the same way,
They're all made the same way. If you take a vase, take your nicest Chinese Ming vase, okay, and drop it on a nice ceramic floor, what happens? It's going to break. And all the pieces are identical, right? No. Okay. So I have an interstellar cloud, and there's stuff going on. There are winds, there's turbulence, there's gravitational fields, magnetic fields, lots of things going on. When it breaks up into little pieces to make stars, some of those fragments are bigger. So we get a distribution of masses of stars. But which ones are the easiest stars for us to see? So if we're not careful, a diagram like this can bias us into thinking that most of the stars are up here. But there's a bias at work, and that bias is that the little faint ones are hard to see. When you work really hard and do a census of stars in a volume of space and count every object in that volume of space carefully, you find that most stars are the little faint ones. And just like when you drop the vase, you get a few big pieces, you get lots of little pieces. So the logic works here. But we also have up here the red giants, and down here we have the white dwarfs, and those objects are not on the main sequence, which means they're different kinds of objects. And they're different kinds of objects because they're in the process of dying. When a star uses up the fuel in its core, it leaves the main sequence. So 90% have the mass of the sun. We're going to call these the lowest mass stars, the little guys. They have enough fuel because they're not very hot and they're not very luminous. They don't use their fuel quickly. They have enough fuel for billions of years. If the universe 500 billion years old, we should find lots of little stars that have died. And there are no such objects. The absent stars that for age, we know the universe is not hundreds of billions of years old. Otherwise, most of these stars would be dead by now. Now, there might have been other ones that were born to replace them on our diagram, but we should still see the embers, the remnants of these stars sitting around. And we don't see those objects. They don't exist. The next larger size, yes, ma'am?
Why should we see them? I mean, if they were dead, wouldn't they collapse into nothing?
Not quite. The question is, why would we see them if they're dead? Wouldn't they collapse into nothingness? The white dwarfs that we're getting to, there's a reason why white dwarfs can't collapse into nothingness. And all these objects, when they die, would die as white dwarfs. And they'll stop collapsing and just cool off. They're going to be our baked potatoes. And then the question of how cool they are. Because as we talked about with the baked potatoes, as they get older, they get cooler. As they get cooler, they're fainter, they're harder to see. So the question becomes, can we see them? And the answer is yes, we could see them if they exist. We don't see them. Yes?
We're measuring the existence, the lifetime of the baked potato from the time you took it out of the oven.
Yes.
What did you put in the oven?
We measure the age of the baked potato from when we took it out of the oven. That doesn't tell us when someone planted the potato, how long it was growing, how long it took to get it to the store, how long it was sitting in my refrigerator before I baked it. So there are a lot of things that affect the age of the baked. If you want to know the true age of the baked potato from the moment it was born, we haven't learned that. So you'd have to estimate how long it takes the baked potato to grow, to be harvested, to get to the store, etc. We can try to do that for the white dwarfs.
A mystery?
It's not a complete mystery. We have some of all these processes, just like we do for the baked potato. It's a really good question. All right. So for our intermediate mass stars, stars like the sun, the sun will use up all its fuel in about 7 billion years from when it was born, which is about 2.5 billion years. So if you're still here in 2.5 billion years, happens when it does. So this is a cartoon of a larger star like the sun. Here it is on the left as a normal star, and down here the red core, that's where the nuclear fusion takes place. The energy is released in the core, it propagates up to the surface, it's emitted. When the star uses up the fuel in the core stops. It just becomes an inert remnant filled with helium. And now gravity is going to start squeezing the star. And now something really kind of tricky happens, because as gravity squeezes the star, what happens to the star? It gets hotter. Even if it doesn't get to 100 million degrees in the core, not hot enough for the helium to turn into carbon, just outside the core, where the temperature had been 9,900,000 degrees, there's a shell around the core that gets heated up and hits 10 million degrees. And that hydrogen in that shell says, well, I couldn't do nuclear fusion last week, but guess what? I can do it now. And nuclear fusion surrounding the core. And because nuclear fusion kicks in outside the core, closer to the surface of the star, there's less material above that layer where nuclear fusion is happening, and it's able to push the outer layers of the star outwards. And even though the star contracts, forced to expand, the star gets bigger. So these objects become giant stars and then supergiant stars. And if a star was here on the main sequence and it starts to die, it expands, which is going to make it cooler, but it has to become luminous because it's resisting greater gravity, because inside it was getting squeezed. So it actually moves upwards and becomes bigger, cools off on the outside, but becomes more luminous. So up here are those red giants, and on our HR diagram that looked like this, these objects up here are all stars that have left the main sequence because they used up the fuel in their core. And now things get really weird. The toughest thing we're going to deal with today, so this is why I said you may not want to come back next week, because you may be unhappy with me. Inside the core of the red giant, weird things start to happen. Inside the core of the red giant, it's super hot, which means I don't have a hydrogen atom with a proton and an electron orbiting the atom. I have lots of protons and lots of electrons, but they can't stay together as atoms. You just have lots of ions. So I have inside the core this sea of electrons moving around, because the electrons are light and small and they just move everywhere. So I have this giant sea of electrons. Quantum mechanics, there's a limit to what you can do with those electrons inside. Remember, the electrons have a temperature. That temperature produces pressure that pushes back against gravity. Thermal pressure is resisting gravity. Gravity is squeezing. As I squeeze the core, the electrons are squeezed into a smaller and smaller volume of space. I'm going to try a couple of analogies with you here. Analogies break down eventually, but we have a bunch of chairs in this room. There are enough chairs that all of you have a seat. If we start bringing in more people, squeezing more people into this room, and we fill up the seats, eventually all the seats will be full. And then if they'll have to stand. That's sort of what's happening inside the core of the red giant. When you have to stand, you would become, in the language of mechanics, you can't find a place to sit. Energy is quantized, which means every energy, I'll have this much energy. I can have 1 unit of energy, or 2 units of energy, or 3 units of energy, but it can't have 3.5. It just can't happen. We can't tell you, physicists can't tell you why physics is that way, but physics is that way. Energy is quantized. And we have everything you depend on for modern science, all your devices depend on our understanding of physics working this way. Energy is quantized. Orbits of electrons around nuclei, the electron can be in this orbit or this orbit, but it can't be in between. Those are the so-called electron energy shells. Energy is quantized. The electrons of the star are being squeezed. All the electrons that can find the lowest energy position they can find. In this room, there might be 10 low energy. And once all those 10 spots are used up, the other electrons can't have that energy. If they go to the next room, there might be some seats at that energy left. But in this room, there are no seats with that energy left. They're stuck now. They can choose to take a different energy. That's what they have to do. They're forced into a higher energy level than they would like to be. It's sort of like a wrestling team. If you imagine a wrestling team and there's the 110-pound wrestlers and the 120-pound wrestlers, 140-pound wrestlers, you're the coach of that team. You've got 220-pound wrestlers who are really good. But you can only wrestle one of them at 120. So you're forced to take the 120-pound wrestler and put him in the 140-pound weight class. They don't belong there, but they're stuck. They're in a weight class in which they don't belong, but there's no choice. The electrons inside the star, just like that. All of the energy seats are taken. They take higher energy seats. Eventually, all the seats are taken. But gravity squeezes even more electrons into their volume. They are forced to jump into those seats anyway because they're the only ones available. Effectively, when gravity can't squeeze any more electrons in there, there's nowhere to put them. So there's absolutely no way to get any more in there. So have degeneracy pressure. And it's a really weird thing. And here's my cartoon, which is sort of what we're talking about. So I'm not going to stay with this. But enough seats for all the electrons. They're there. So they're forced into these higher energy levels, which pushes back against gravity. Gravity can't squeeze the star anymore. The pressure that's now resisting is not due to heat. It's not because the center of the star is hot enough to resist gravity. It's because the center of the star has too many electrons in too small a volume, and it can't get any more in there. So it stops gravity. It pushes back. And now the star is in balance. This is called the Pauli exclusion principle. That's the idea that there just aren't enough seats at the table. Okay? And you've got to force the electrons into the high energy level. Okay? So this provides our pressure that we need for this gravity. The important key here is that pressure is not linked to heat. It's now independent of heat. It doesn't matter how hot the star gets, the heat doesn't matter. It's the degeneracy pressure. But it's just the core of the star. Just the core. So now we have inside the red giant, we have all this stuff occurring in the outer layers. We have hydrogen turning into helium. We have a shell where helium might be turning into carbon. But deep down in the center, we have this degenerate core, mostly made of carbon and oxygen, that's just sitting there doing nothing. And it can't get squeezed any further. And eventually, the heat being generated in the outer layers of the star pushes the outer layers off into space. So our star was up here as a red giant. It pushes the outer layers away like a smoke ring. The outer parts of the star just go off into interstellar space and disperse. And what's left at the center is going to be a white dwarf. Here's some of these so-called planetary nebulae have nothing to do with planets. They are red giants that have pushed off their outer layers until all that's left is the white dwarf at the core. This one is known as the Ring Nebula. This is the Hourglass Nebula, the Cat's Eye Nebula, the Twin Jet Nebula. But in all of them, at the core, a white dwarf is being left behind. The white dwarf is the core of the dead star. It's not hot enough for fusion to take place. But it can't be shrunk. It can't be crushed by gravity because degeneracy pressure resists gravity. So now I have my astrophysical baked potato because I have an object that can't shrink. And I have an object that's so it's giving off to space, but it has no source. So it's just going to cool off. And those white dwarfs on the HR diagram are just going to, I wanted to stay right here. Because white dwarfs are just going to, they're left behind inside the planetary nebula. They have no heat source, so they have to go downwards. Okay? Initially, what we see is hotter because the exposed layers of the star expose that really hot core. So it moves over to the left and gets hotter, but it gets less luminous, and now right here is when the true white dwarf emerges, and now all it can do is cool off, but it can't shrink. So it gets cooler and less luminous. Shrinking would mean moving downwards and to the left. Going downwards at this angle means staying the same size and getting less luminous. What we have left behind is this degenerate core of carbon. It doesn't have enough mass to get hot enough for nuclear fusion, so it has no energy source. Gravity is stopped by degeneracy pressure. Gravity loses. This object is dwarf for the rest of how long that may be. There's nothing. Of the dead star, and these objects are stable, okay, because of the balance between gravity and pressure. They're incredibly dense. It's the mass of the sun, but the size of the Earth, and they can't shrink, so that's why we have our white potatoes. The white dwarf is hot. It emits light from its surface. The heat from the surface is replenished by heat from the inside, which means the whole thing gradually cools off. But because they're small, it's like the small burner on the stove, they cool off slowly, not quickly. The cooling rate, remember, the amount of energy we get out, we said from the Stefan-Boltzmann law, depends on size and temperature, but the size doesn't change, so it only depends on temperature, which means as it cools off, it has to become less luminous. All right. So those words just describe this sketch again, that the white dwarf just slides down this way as it cools off. We now have astrophysical baked potato, and we can try to measure white dwarfs. All we have to do is find them, and we find lots of them. The oldest white dwarfs will be the coolest white dwarfs. The oldest white dwarfs will be. We have to look for faint and cool white dwarfs in order to find the old ones. We can calculate how cool a white dwarf would be if it were 50 billion years old, 100 billion years old, 20 billion years old. How long an object has been a white dwarf, in the same way we can calculate how long it takes the potato to get out of the oven. That doesn't tell us how long it took for the object before it became a white dwarf. So we have to add that to the age if we want an actual age. So here's a tough plot to figure out, but you can do it with me, and then we're just about done. Just a look of the unit. You don't have to worry about that. It's called magnitude. The horizontal axis is just temperature. It's measured in some other units called color. You don't have to worry about that. These are the white dwarf tracks, these cooling tracks. The 0.6 m right here means 60% of the mass of the sun. Down here, 1.2 m, that means 120% the mass of the sun. The more massive the white dwarf when it's born, the smaller it is. Because gravity, more mass squeezes it, so it's become smaller. More massive white dwarfs are small. It's an odd kind of thing. Once a white dwarf becomes a white dwarf, it stays the same size, and it just slides down these lines. These symbols right here, these black funny-shaped symbols, come from one different group of stars. Each dot is a white dwarf. The white dwarfs in that group of stars were not born at the same time. The ones that were born first have had more time to slide down. The ones that were born more recently are still up here, but they're all from the same group of stars. They're all about the same size of stars. This one down here is 9.3 billion years old. That's how long it's been since that object was born as a white dwarf. This triangle right here comes from a group of stars that are 8 million years old. It took 8 billion years, for that star to get there. The very oldest white dwarfs found are about 30,000 times fainter, and they have temperatures about 4,000 degrees. They have ages as white dwarfs of about 11 billion years. We then have to calculate what was the age of the star before it died to become a white dwarf. Well, we know the star lived for 7 billion years. The question is, how long could these stars have lived before they became white dwarfs? All stars that are currently white dwarfs have to have started with at least a minimum mass that's bigger than the sun, or they would still be stars. But those objects have lifetimes of only a couple billion years as main sequence stars, regular stars. Do that. That one's going to take too much time, right? The very oldest white dwarfs we found are the one I mentioned, this guy. That's its name. It's about 80 light years from the sun. This is its temperature. That very oldest star has an age as a white dwarf of about 12.7 years. Searched incredibly hard for fainter, cooler white dwarfs. If there our telescopes are big enough and powerful enough that we've found them by now. They're not there. They simply don't exist. So no object has been a white dwarf for more than this amount of time. There's no object that's been a white dwarf for 14 or 15 or 20 billion years. And it'd be a pretty funny universe to have spent 100, 400 billion years waiting around thinking, well, I think we're going to wait for 400 billion years and then we'll make a white dwarf. More likely, some white dwarfs were made as soon as it was possible for them to be made, which means the universe is much older than this. The best estimates for the amount of time it took to grow the white dwarf, the baked potato planted in the ground, harvested, brought to the grocery store, is about 1 billion years. So we get from this an estimate that the universe is probably about 14 billion years old. Older, we would see would be fainter than these, and they're simply not there. But for a real age of the universe, it gives us a ballpark. Yes, sir.
Why don't these things deteriorate until the point that they're so faint and so cool that they're still there, but you just can't see them?
They should. That's exactly the point. They should cool off from degrees to 29, 20 to 26 to 26. They should become 4,000 degrees, 39, 38, 37, 36, 30,000 degrees, 2,000 degrees. We should see a white dwarf with a temperature of 3,600 degrees. We can see a white dwarf with a temperature of 2,500, of 2,000 degrees. There are no white dwarfs out there that have gotten to that point. The universe is not old enough. But eventually, indeed, fall apart, we literally can't see them anymore. So there ought to be white dwarfs that are invisible, and white dwarfs that are incredibly faint, and white dwarfs that are a little bit brighter. There's no continuum beyond these, which tells us there's an upper limit to the age of the universe. And that upper limit is of about 14 billion years. I think we can take a couple questions. Yes?
I had heard black holes were created by suns that collapsed, where no light could get out of them.
Bingo.
So, is that correct?
That's correct. We haven't yet become white dwarfs. The intermediate mass stars, sort of like the sun, a little bigger than the sun, that can become white dwarfs. The biggest stars, the most massive stars, stars like Betelgeuse that we saw, Rigel, these are big, massive stars. When they die, they'll become black holes. There are 3 fates for stars at the ends of their life. Whereas the little guys can become black holes. They can only become white dwarfs. Intermediate guys can become white dwarfs black holes. The exactly what happens. So yes, stars can use black holes, but not these guys, just the big guys. But they're out there, yes.
I missed how you arrived at the determination it took about 1 billion years from the time the process started to become.
I didn't tell you. That's why you missed it. The way we get that is we talked about today. We're going to talk something about those next week. If this star had a mass twice the mass of the mass of the sun, then I know what its lifetime would have been on the main sequence before it died, before it became a red giant. And I know how long that star would go from the main sequence to the red giant, a planetary nebula, and a white dwarf. So I can take the age of the white dwarf, get to become a white dwarf after it left the main sequence. I can add to that the amount of time it spent living on the main sequence. Then you have to ask, how long was the stuff around in the universe before it decided to collapse and make the star that became the star that became the question? Yes. Yes.
Class that you taught a couple of years ago, I asked you a question that had been bugging me a long time.
Did I answer it?
Yes.
Oh, good.
You enlightened me tremendously about a lot of things. I asked you for a definition of gravity, and you told me that it had to be an operational definition. And I think that applies to almost everything in life. Everything
I was young and
in
smart
life.
then when I gave that answer.
An operational definition is what you're giving here.
Yeah, all of this is very operational. I can't tell you why gravity exists. I can't tell you why quantum mechanics rules the structure of small particles. But I can tell you this is the physics of the way the universe works as best as we can understand it from all the experiments that all scientists have done collectively over hundreds of years. But yeah, it's operational. There's another hand over here. Yes?
If the star's cooling off, that means the gravity is succeeding,
Yes.
gravity is pushing stuff together. If it cooled off enough, would the gravity eventually make all these electrons and stuff become solid?
If the object cools off enough, would gravity just squeeze the whole thing into one solid thing? That's the question. If gravity is strong enough, electron degeneracy loses. Even electron degeneracy pressure is not enough strength to resist gravity if the mass of the object is great enough. And then gravity will take the electrons, which are trying to hold off gravity, and it'll squash those electrons into the protons and turn them into neutrons. And now you've got a neutron star. And now the whole thing is much smaller. And now you have a neutron degenerate object. And now neutron degeneracy can try to resist gravity. If gravity is so strong that the neutrons can't survive, gravity just crushes the neutrons. And the neutron quark degenerate object. But a quark degenerate object would be so small, in which case we have no idea what's happening in there, because the light doesn't get out, the information doesn't get out. So the answer to your question is sort of yes.
Charged protons resist each other. Do not the negatively charged electrons also repel each other?
They sure do, but we just don't care about the electrons. They're not going to participate in the nuclear fusion. They're not the active fusion part of the inside of the star.
I understand a little bit about the quantum physics and the orbital theory of the electrons and the specific energy bands and so forth, but that's when they're surrounding a nucleus. When they're in this degenerative state, what is the difference in the energy state?
Okay. Ourselves if we say it's easy to understand. can understand conceptually that there are these energy levels the electrons can occupy. When they're not in orbit around the nucleus, why are there energy levels? There still are. There's the lowest energy anything can have. You're sitting there. Well, you could be lying on the lower energy level. You can't get below that. If I took all the chairs, the floor is filled with people and there's nowhere else on the floor to lie, and someone else comes in the room, they're going to have to lie on top of you guys. All right? Still quantized energy levels. The electron has no choice. Whatever place it's at, there's still a limited number of energy levels it can have.
How does it manifest the energy? Is it literally that it increase in speed, or is it emitting photons, or what?
Well, it's really just how it's moving. It's how it's moving, it's how it's spinning, it's how it's doing a number of other things. But that's a pretty tough question. I'm going to pretend you didn't ask.
Is the total energy in the universe constant?
Total energy in the universe constant? Probably, but we couldn't prove that one to you. Okay, but the energy shouldn't change. But the energy can change reservoirs. So you can change energy from kinetic energy to potential energy to electromagnetic energy, chemical energy to mass. But the total amount of energy shouldn't change.
But it's an assumption to begin with.
That's an assumption to begin with, yes.
Where do the nova fit into this scheme?
Where do the nova fit in? Novae and supernovae. Supernovae are the stars that die and explode at the end of their lifetimes. Novae are littler stars that kind of burp regularly and get brighter and then do it again. Okay. So they're both stars that are dying in different ways. Last question.
All masses have gravity?
All mass has gravity. Thing with mass. Asked to mention, some of you asked if the bookstore folks are going to be here today. They're not. If some of you want, they can come back next week or another week. So if there's enough clamor for that, we'll ask them to come back. If you want that, mention it to one of us and we'll let them know. Thanks very much, and we'll see you next week.